Hi everybody, in this video we are going to go over section 3 of chapter 8, and in this section we are going to estimate population means or compute the confidence interval for population means for the case where we don't know the population standard deviation. Okay, so once again, here is our confidence interval. And remember, our confidence interval contains two parts, basically the sample mean and the margin of error. The margin of error is primarily determined by our level of confidence. So if we already know what the sample mean is, the confidence interval is all about trying to figure out what that error is. Now, for the case for the situation where the population standard deviation is known and you have a normally distributed population, this is our equation. Basically, E is going to be equal to our critical value times our standard deviation divided by the square root of n. Our critical value is determined by our confidence interval, namely, if our confidence intervals are here, then the associated critical values are here. Relatively straightforward. Okay, well, in this particular case, we do not know what the population standard deviation is, which is typically the normal case. Therefore, if your sample size happens to exceed 30, or if your population is approximately normally distributed, then we can compute E using this, where in this particular case, this is the critical value associated with C. However, notice it says T there, and this over here is the sample standard deviation. And our critical value here is found using the T distribution. Specifically for a given level of confidence, okay, and the confidence is going to be the area in the middle. Alpha is going to be, which is equal to 1 over C, is going to be the area in both of the tails. Alpha over 2 is going to be the area in exactly one of the tails. And the critical value is going to be that value of T that produces that results in that area to the right. Once again, for T distributions, we need to know what the degrees of freedom are. In this particular case, the degrees of freedom will always be will always be equal to the sample size minus 1. And the best way to show this is, you guessed it, using an example. So here's our first one. A random sample of 14 fields of barley has a mean yield of 26.2 bushels per acre and a standard deviation of 7.1 bushels per acre. Determine the 99% confidence interval for the true mean yield. Assume the population standard deviation is approximately normal. So how can you tell if this should be a T distribution problem or a C distribution problem? And the key is right here. Notice nowhere here does it say population standard deviation. It just says standard deviation. 14 fields of barley gave you a standard deviation of 7.1. Since the word population is not there, this is a T distribution problem. Okay, that's the big thing you want to know. So now we need to find the critical value that should be used in constructing this confidence interval. Well, first thing we need to do is we need to start with C. C is 0.99. Therefore, that's the area in the middle. The area in both tails, alpha, is 0.01. The area in one tail is going to be 0.005, half of that. Degrees of freedom, since we have 14 samples, the degrees of freedom happens to be 13. Once we know that, we can go to our tables, okay, and we can go ahead and look up. We go to this column for 0.005, this row for 0.13 or for 13, and this will be our answer, 3.012. Okay, so that takes care of part A. Now, part B is to go ahead and construct that confidence interval. Of course, since we're using the T distribution, we're going to be using this formula here. It's pretty much the same formula, except that instead of having Z, we have T, and instead of having sigma, we have S. Turns out that our critical value from part A is 3.012. Our sample standard deviation happens to be 7.1, 14 samples. This gives me 5.71. Now keep in mind that our rounding rule is that our error needs to have the same number of decimals as our standard deviation. So we can round this to 1 decimal. And once we've done that, we will have, and also noting that our sample mean is 26.2, we have that our lower limit is going to be 26.2 minus 5.7, 20.5, and your upper limit is going to be 31.9, or 26.2 plus 5.7, 31.9. Now, how can you compute this using our calculator? I'm going to go ahead and show that here. The first thing I want to do is, let's go ahead and do, is not this, but to go ahead and figure out what t happens to be. So here's my calculator, and to figure out what t happens to be, what we need to do is we need to go into, in other words, our critical value happens to be, we have to go into distribution, namely second VARS, and we want to go to inverse t. Okay, so we want to find that value of t, where the area to the left, to the right of it is 0.005 and it has 13 degrees of freedom. And conveniently, I already have this here. So our area is 0.005, degrees of freedom is 13. We go ahead and paste, and we get an answer of negative 3.012. Keep in mind that this function finds the values to the left. Also keep in mind that our critical values will always be positive. And if that's the case, then we can just ignore the negative sign and we'll have 3.012, which is exactly what we got before. There you go. Okay, now the next part is to figure out what t is using our calculator, or figure out what our confidence interval is using our calculator. Now to do that, we want to go into stat. Go over to tests, and notice down here we have t interval. That's where we want to go. So go on down to 8, hit enter, and we want to make sure our input data is on stats. Here we have our sample mean of 26.2, our sample standard deviation is 7.1, 14 samples, my confidence level is 99%. I can go down to calculate. And after rounding, we get the exact same answer we had before. 20.5, 31.9, which is exactly what we were looking for. Okay, so that takes care of part of our first example. What about our second example? Oh, here it is. Here we have a physics examines four seawater samples of potassium chloride concentration. The mean potassium chloride concentration for the sample data happens to be 0.604 cubic centimeters or cubic centimeters per cubic meter of water, with a standard deviation of 0.0177. And we want to find the 80% confidence interval for the potassium for the population mean potassium chloride concentration. Say that 3 times fast, and we want to assume the population is approximately normal. Once again, since the word population is not around here, this is not a population standard deviation. This is a sample standard deviation. I know that because the word population is not here. So this is going to be a t-distribution problem. Okay, so to find the critical value, first we need to figure out what alpha over 2 is. Well, if c is 0.8, then the area in both of the tails is going to be 0.2. The area in exactly one of the tails is going to be 0.1. Since we have 4 samples, our degrees of freedom is going to be equal to 3. So now we can use our tables to figure out what that is. Okay, 3 degrees of freedom, 0.1. That gives me 1.638. Which is exactly what we have here. Okay, for the next part, we want to construct the 99% confidence interval and round our answer to 1 decimal place. Okay, cool. Well, we're going to use this equation for E. Once again, we know what S is, we know what T is, we just figured that out. So this is T, this is S, square root of 4. This brings us we obviously don't want to round our answer to 1 decimal place. That's not going to make any sense, so forget about that part. But this brings us down to 0.01456. We're going to round this to 4 decimal places like here. So we're just going to ignore that, because if we don't, we're going to have basically no interval whatsoever. So our error is going to be 0.0145. And if that's the case, then the lower limit is going to be our sample mean minus that, 0.5895. And then our upper limit is going to be 0.6185. So I guess we could round it. Now here, we could round our answer to 1 decimal place. We will just simply have 0.5 and 0.6. Okay, and this brings us to our last problem. Here we have a toy manufacturer wants to know how many new toys children buy each year. A sample of 520 children was taken to study their purchasing habits. Construct an 85% confidence interval for the mean number of toys purchased each year if the sample mean was found to be 6.6. Assume that the population standard deviation is 2. Round your answer to 1 decimal place. Now notice here, in this particular case, we actually have that this sentence actually says that the population standard deviation is 2. Since we know, which means we know what sigma is. Since we know what sigma is, this is going to be a z interval problem. Not a t interval, but a z interval. Okay, so what is the critical value associated with constructing with constructing the confidence interval? Well, basically what we want to do is you want to find in this case we want to use the z value. We want to use the z value for the case where c is equal to 0.85 or 85%. And if we looked up in our table, or if we looked up in the table that we saw earlier, we would find that our critical value is 1.44. Once we've done that, we can now solve the rest of the problem. Okay, construct an 85% confidence interval. Round your answer to 1 decimal place. Okay, since we're doing z distributions, we are going to use this particular equation, substituting 1.44 for z, 2 for sigma. N is 520. We get an error of 0.1. Okay, and that means that our lower limit is going to be 6.6 minus 0.1, 6.5. 6.6 plus 0.1, 6.7, and we are done. And that is all that I have for this particular video. Stay tuned for our next video, where we will do the homework relative to this section. And until then, this is Bob Boyle, signing off.